Okay. Um, Good afternoon, ladies and gentlemen. I would like to invite you for the second session. I would like to start to introduce our respective professor. Professor Pan Lianxin was born in Xinjiang, China. He received his bachelor degree in 1985 and then his master degree in 1988 in the chemistry from Xinjiang University in China, and his PhD in 2000 from the National University of Singapore. He worked with Professors Omar Yaghi at the University of Michigan, Stephen Lee at Cornell University, and Andrew Magwerk at Louisiana State University as a postdoctoral fellow between 2000 and 2003, before joining the University of Texas Pan American in 2003. Professor Chen moved to UTSA in August 2009 and was promoted to Professor of Chemistry in 2011. He has published more than 180 scientific papers in premier journals such as Science, Nature Communications, Angewandte Chemie International Edition, Journal of American Chemical Society, Advanced Materials, Energy and Environmental Sciences, Chemical Reviews, Chemical Society Reviews, and Accounts of Chemical Research with over 20,000 citations. In addition, he holds 11 patents, one licensed and another optioned. In 2011, he has ranked as one of the top 100 chemists over the past decade based on citation impact factor. In 2014, he was chosen as a highly cited researcher with 33 highly cited papers over the past decade and one of the 198 highly cited chemists. He was spotlighted in the world's most influential scientific minds in 2014 by Thomson Reuters. So I would like to thank you, and we're looking forward to listen to your impressive lecture.
Thank you, Dr. Mustafa, for the introduction. I'm very happy to be here, and also meet my senior Muhammad, and our old friend and new friend. So what I talk about today is about the middle organic framework as a platform for multifunctional materials. And you know, discoveries of new material are very important for the development of science and technology. Also, yes, a little bit weird. Also, some material also closely related to our daily life. So discover of some material can improve our quality of life. So this apparently is very important. And it has also been demonstrated in several Nobel Prize in chemistry, in physics, and in physics as well, discover different kind of material. Also, we're not so sure the pioneers in morph scientists, chemistry will get a Nobel Prize or not, but apparently morph is a very hot topic, and actually even Omar Faha has a company to try to mobilize some, commercialize some material, and morph methane storage gas tank has been already on board by BASF, so eventually, hopefully, can be utilized for our daily life. And also, the research topic is very hot, as I demonstrated in two seeing the reviews. So today I will basically briefly introduce the morph history, and I think it's still very important. Some of you are not so familiar with this field. I think we always can learn quite a lot from the history, and then I will talk about why morph materials are very useful platform for multifunction materials, and I will briefly present some of our examples of multifunctional materials in our group. So, so you know the porous material is very important. Actually, Garcia and their group are working on a lot of these zeolite materials. Some material have been commercialized, and this is also another very famous from a scientific point of view. The Prussian balloon, here is a bridging is the cyanide, and here the zeolite basically is we call the aluminum silicate. So the node is aluminum and silicate, and the linker is the oxide hydroxide. And so these inorganic component can be utilized as a linker to construct a polar material. And actually, a long time ago, a lot of scientists tried to working on different kind of inorganic component like sulfide, phosphate, and even organic phosphonate has been utilized during later time to try to construct the porous material. Although this approach was not so successful, but apparently has been dwindling the possibility using these organic components. So from other kind of coordination chemistry point of view, actually this is a very old compound, the coordination compound well established, and actually a few even molecular compound can take up some gas molecule, because it is very important to take up some gas molecule or vapor. So, and furthermore, the coordination polymer here, basically coordination polymer, some structure of coordination polymer has been well established. So it seems to be quite natural, although the concept to use organic linker to try to stabilize the framework to establish permanent polarity was kind of proposed during this period. And at the beginning, because this is structurally porous but not stable, so what means once we remove the solvent molecule, the framework collapses. So no any gas absorption property at all. And at the beginning, a lot of effort to try to stabilize the framework. One of the methods is try to, using these pi-pi stacking interactions. And this work is certain extent is kind of robust, although no gas absorption, vapor absorption has been established. This is another example. And in fact, this is the first time I think Omayagi turned this metal organic framework. But in fact, this one actually basically is stable with the solvent exchange. So here is the benzene or pyridine can be exchanged with each other, but still not the gas or vapor absorption properties. So some significant progress was realized during this period. This is one example. The structure is two-dimensional, but here the absorption has to be realized under very high pressure. So because the optic is very, very low, but still it's one quite important progress. And this is very important. So Mohammed here, and he made the most important contribution to establish this permanent porosity. And this structure two-dimensional, and this is a very important structure, although the porosity here is about 500 meters square. This is another example. That, of course, the most important contribution certainly is the breakthrough in this field is this one, MOV5, the most famous. And apparently, this material can be easily synthesized by this organic linker, BDC, and zinc nitrate. And so the highly surface porosities immediately attract the passive collaboration. So this is a breakthrough, certainly. Mohammed also established these high porosities. And so I joined with work with Omar, so we use a very simple synthesis approach using solvothermal approach. Basically, before this work, the original MOV5 is a little bit complicated to synthesize by the diffusion technology, so it takes a while. So this solvothermal is very simple, so we can synthesize the material within typically 1 day and to get a very nice crystal. And also large linker can be incorporated into MOV material. And this linker is kind of large, so the pore has been interweaving. So basically, it's a two framework identical one interweaving with each other, but this still porous. So Mohammed also helped to establish the permanent porosity. And during this time, another scientist even wrote a commentary, perspective comment, the simplicity of complexity. This is a nice word. So basically, the synthesis is kind of simple, but we can produce kind of interesting complex materials. So to certain extent, the methodology to synthesize the MOV material has been established. So the question here is why MOV material can be developed as a MOV material, multifunctional material. Actually, there are two SES symposiums that are called MOV, what are they good for. So now we consider both the porosity, because so basically most are self-assembled in the framework from metal ions or metal clusters and organic linkers. So because a lot of different organic components can be assembled into the porous material, so there are some different features. The pore can be easily tuned from small one to larger one, and some functional side can be immobilized on pore surface. So we can use this porosity for different kind of recognition and for gas separation and storage. On the other hand, because this is also we can consider as a hybrid material from the inorganic components and organic components. So basically all the properties, physical or chemical properties or inorganic component and organic component can be incorporated into this hybrid material. Or we know the optical material, electronic material, or magnetic property. So beyond our imagination, first of all, the pore can be utilized to capture different kind of species, can be nanoparticles, or dimolecule, or ions, or whatever. So functionality can be developed. So very straightforward. So I just show you some examples on different kind of applications. So summarize. This is the first one. I started my independent career. So the work is have some impact. Basically, one is the concept of this open middle size. Actually, this open middle size was generated several years ago. So, and secondly, this metal dicarboxylate unit turned out to be a very useful building block for the construction of this metal organic framework. So this, and of course, the structure kind of predictable. This is a square planar. This another square planar to have an niobium oxide structure. So we realized that when we remove the solvent molecule to have an unsaturated middle size, the uptake of a gas solution is significantly enhanced. So this conceptually is important. And for acetylene storage, initially we realized by Suzumi Kitagawa, so this material is kind of small pore, so limited it is uptake. This uptake is quite low. So we realized that from use different kind of porous middle organic framework. Apparently, highly porous one is not so efficient because this storage needs to be realized under very low pressure. Basically, here is 1 bar. So this space are not be utilized for uptake, very low. But when we narrow down the pore, the uptake can be increased. And these two more are specific because they have open middle size. So the open middle size enhances interaction with the acetylene. So the overall, this uptake is very high. This liquid one. And furthermore, we even established the binding site and by neutral diffraction studies, clearly indicating this open middle size to bind with acetylene. Although the binding is still not a chemical binding, is a kind of a strong Columbus interaction. So this side is very clear. So now we can further enhance the acetylene uptake by immobilizing more open middle size and a little bit stronger interaction. So we realized that this Morpho 74 series is very suitable for acetylene strategy. So we have another record acetylene storage material. Actually, acetylene is also one of very potential fuel for our vehicles. And methane storage actually, yes, Adadi is the first author for the science. So here, and so gravimetrically, what I mean gravimetrically is per gram of sample, the storage amount of methane can be very high, basically because the storage capacities are proportional to the porosities. But there's an issue here is for those highly porous morph material, eventually the framework density are quite low. So overall, there's a balance because we have very limited space, the trunk, to storage methane. So the best ones is for the magic high density for the methane storage. So with a limited space, can storage large amount of methane. So that's our focus. And Joe made a kind of important contribution, and Omar also repeated the work that basically this pore is kind of specific, so kind of tuned. So we use a very simple and very small tetracarboxylate, and similarly with this paddle wheel, so the structure is kind of predictable. The uniqueness of this material is there's a kind of high density of open middle size because the open middle size is the primary binding site of methane. Furthermore, this pore surface is a pore cage is kind of suitable. So you were showing here that small cage can capture 3 called a methane, and each open middle side can bind one methane molecule. So overall, this material can store a high density of methane. So this work has been optioned, the patents are optioned to multinational companies. And nowadays, it would be good if we can establish an empirical formula for methane storage. The reason is the high pressure absorption data sometimes are not reliable because of the sensitivity of this kind of instrument. In fact, only a few reliable instruments are available right now. And also we can easily get porosity from absorption studies. So if we can, from this data, we can make some prediction, then we will facilitate our screen. We can screen some material first before we do detailed studies. So basically here is the saturated one. Basically the saturated one is proportional to the pore volume, while the pore occupancy, so the pore occupancy definition of pore occupancy is the storage amount at this storage conditions divided by saturated one, we call the pore occupancy. So this pore occupancy is reversibly proportional to pore volume. It is understandable, the larger porosity, the less pore occupancy. So based on this equation, we can figure out this empirical formula. It turns out that the matches with experimental one quite well, around within 10%, I think is quite well. And furthermore, in fact, we were even able to kind of predict the literature data, because the Hong Kong UST one is one of the most famous one, but different groups have different property report, mainly because activation is very sensitive, and we realize that this is the best one in terms of porosity. So based on this, we expect from our empirical formula we can take up this amount, and it seems match quite well with one of Omar's work and with another Long's work. So it can help us to screen material. And recently we also realized that it's an empirical formula under 65 bars. But it's still very challenging to increase the storage capacities. So this is quite an older one. So we actually quite accidentally realized that immobilize these pyramiding of size can enhance the storage capacity. And at this moment, the reason mechanism is still not so sure. But the one thing I want to mention is that this significant increase the storage capacity about 30 cc. This is quite significant. And furthermore, this material has a record we call the delivered amount, the working capacity. So the working capacity definition is the storage capacity under storage condition minus this storage capacity under basically 5 bar or 5.8 bar, because it is not convenient and energy cost to remove all the gas under to 0 bar. So the difference we call working capacity, this is quite high. And we use different kind of size, systematically. We show that this uptake can be tuned systematically. So indeed, this functional size can help to enhance the storage capacity to a certain extent, but still very, very challenging. So the second part about gas separation basically is tuning of the pore is very important. So this figure indicating how, like building a small space. So the linker becomes shorter, the pore can become smaller. This is obvious. So the sieving effect is one of very important factors for separation of gas molecule. So this is a very simple example using this format. So with a copper parallel to form two-dimensional sheet first, and these two-dimensional paired by different paired organic linker. So you will see that pyrazine, this is a condensed structure, and then the pore is slightly increased, and so this one a little bit large is about 3.8, I think. So this is suitable, so that we'll allow hydrogen to go through a channel where methane and nitrogen sometimes will be blocked. So it's also can be utilized for carbon dioxide capture separation. So this is a conceptual. And then we use another linker we call the BDC, benzene dicarboxylate, with this bipyridine. So the pore is a little bit larger. Here is about 4 angstrom. So the 4 angstrom is basically the missing size is about 3.8 angstrom. So basically it's comparable with the linear part of alkene. So we pack the column, and the column can easily separate the natural gas isomers. So basically here is because the longer the least interaction strength is depend on the length of the linear part. The longer the least linear part, the stronger the interaction, the slow this arcing goes through the channels, so through the columns. So this can be also utilized for separations of pending isomer and hexing isomer. So it's quite straightforward. And in the separation can also be enlarged at the fixed bed absorption. So eventually we need to use a tower for separation, separation. So very potential. And we also realize that this we call the meta ligands. So this ligand has some uniqueness. So this open middle size and also this linker. And this linker can finely tune the pore because the pore is very important, fine tuning. And also we can incorporate this calodiamine. So the pore are callow for initial selective separation. So this example, this first example, we call the mixed middle organ framework. And this work has some significance. One is that this each metal side can bind two gas molecules because it's very unusual. And each typically open middle side is easy to be saturated, binded by another organic linker. So, but two is kind of interesting. And secondly, the binding energy is kind of high. Is over 12 kilojoule per mole because eventually hydrogen storage, the most challenging one is this adsorption entropy. So entropy if can be increased, then the storage temperature can be kind of increased for the hydrogen. So this is one of the challenges. Also, this can be for kinetic separation of hydrogen and deuterium because the diffusion rate through the morph material are kind of different. So. And you see, we use calodiamines, and this cavity is callo, and specifically recognize one of the isomer, so it can be used for separation. And we realize the first examples of morph material for acetylene and ethylene separations, although here the uptake is not so high, but selectivity is kind of high. And as we mentioned, we use a different diamine, different functional group, different carboxylate, so the pore can be kind of tuned. So optimize the separation capacity. Again, this separation selectivity is okay, but uptake is not so high. And almost a little bit later than Long's work, we also realized the morph 74 magnesium one for the separation of these four components. And this one actually, the uptake is high, actually, acetylene and acetylene, because they have high density of middle side, as mentioned, for acetylene storage capacity, storage. But here there's a problem is because the open middle side also combine both acetylene and ethylene. So the selectivity is not so high. So that's the opposite one. So the first one is the selectivity is okay, good, but the uptake is not good. But this one uptake is quite high, but the selectivity is not. So the ideal one actually, because of the column, so the ideal one is the morph material can take up a large amount of acetylene. Also selectivity are high. This is the best one for the separations. So we realize this is kind of unique example of morph material. So this morph material have quite a unique pore, basically about 4 angstrom. So the selectivity is quite good. Furthermore, some of these kind of small cage are kind of useful because only can take up acetylene. So overall, these materials have a moderate high porosity and also uptake. So separation here is much higher than other type of material. So and further confirmed by experimental breakthrough. So this is kind of related with productivity. So this is kind of unique example. And carbon dioxide capture is kind of challenging for post-combustion applications, mainly because only one bar. So the high pressure one actually, because the high porosity will of course will enforce the high pressure separation, but the low pressure is kind of challenging. We kind of accidentally realized a unique material UTS 16 for this carbon dioxide capture, and this is quite a high. Although later on, Mohammed also reported several very high material for this carbon capture and separation. So this high, of course, will enforce these separations. So for scientists, we need to know the mechanism. So actually, one more thing I want to mention, this is a very simple citrate, a very cheap organic linker. So the uniqueness here is the pore is quite unique. And neutral diffraction study indicating that this terminal water molecule also play quite an important role for their specific recognition of carbon dioxide. So, and this cage is quite suitable, only about 4.5 angstrom, but it can capture 4 molecules of carbon dioxide. So overall high density of carbon dioxide. So that is a feature. So we can also use this as a hybrid material, and a luminance material lanthanide can be incorporated. So there is the over middle size, and the luminance properties are very sensitive to different solvent molecule. So this is example, first example indicating that addition of acetone significantly quenching the luminance. So once add a small amount of acetone, the luminance quenches. So conceptually, establish the feasibility as a luminance center. And on the other hand, this fluoride can stabilize this terminal methanol molecule, so enhance the luminance properties. So these are still conceptual and also can be utilized for the cation sensing. And this is another one. This basically is not a porous material. It's a coordination polymer, but it is we know the lanthanide, the metal organic framework coordination polymers. We can easily to synthesize isostructure. Different, we can use doping. So we dope one component of terbium or European into terbium morph materials, and then we have 2 luminance centers, and they are temperature dependent. And based on that, we can establish a linear relationship with the temperature. So here, basically 2 centers luminance. So without any collaborations, robust and reliable. And furthermore, we can use different organic linker. So the transition T1, S1, this energy transfer can be tuned, so the sensitivity can significantly enhanced. So this actually quite an interesting example. This is not a beautiful metal organic framework, but useful so for certain exam. And this is quite robust. We can going down, going up, so sensitivity still be very stable. We can also incorporate these pairing molecules, and they're different center. One center, luminous center for our metal organic framework, and another center for our this gas molecule. So we can still use these 2 luminous centers to get a reliable thermometers. So this and to use this pore confinement, these cations can be exchanged by different dye molecule, because these dye molecule potentially have nonlinear optical properties. But apparently, these pore have different effect of pore confinement effect. And turns out that this long Oaking chain will fit this pore. So the orientation of this dye molecule within this 1D channel is well ordered. So the nonlinear optical can be optimized in this case. And then furthermore, we can also use other type of dye molecule, potentially have lasing functions. So here we can exchange, and we see under dilute conditions, these molecules are oriented. And this orientation and pore confinement significantly diminish the quenching effect. As we know, is this easily quenched in the solution or in the solid state. So the luminance property is significantly much higher than those in the solution and the powder. So this enhance it is a potential application for lasing application. So we realize the lasing functions, 2 photon pounder lasing is quite stable, and you see this lasing, of course, is dependent on the length of these crystals, and this is the first example for this finding. So apparently, these low energies of can generate high energy of lasing. So I think it's quite interesting, and also we can use a photoactive organic linker. So this is basically only responsible to the 2 photon UV. So basically, we can use a light, and then once the organic linker are being lighted by this light, then the color will change. So certain extent, we can read this morph material. So this is the case, and so this is for potential for storage. Storage. So basically, so overall, it basically means morph material very potential multifunctional materials, and this I will jump. This is another one about Hoff material for their potential application. Hoff material is even more difficult to be stabilized, and we are a first group to establish permanent porosity for their separation, the calor. So that's it. So overall, we have a lot of collaborations and a lot of friends. So help to have the work done. And finally, I will. And this is fourth group members, and my wife, I need to thank her of all. She is not my group member. Anyway, so I thank you for your attention.
Thank you again for your impressive lecture. And I would like to open the gate now for questions. So, please.
In the page 60, you're encapsulating the dye process. It looks like you're talking about upconversion, right? It's like low.
Yeah, right.
Yeah, it's an upconversion process.
Right,
Can you explain a little bit more about why this material has an upconversion property?
The mechanism, in order to generate lasing, we need to have a kind of a suitable cavity. So the suitable cavity, I think, is quite good. So this is a kind of is a cavity, and so the reason is because these dye molecule also have a two-photon activities. So two-photon can generate. So basically, long wavelengths can generate a low, high energy of wavelength lasing. So originally, this dye molecule has this property. So here, the pore basically try to confirm. So the luminance property has been significantly enhanced. The quenching effect has been diminished.
So the dye itself already has upconversion property.
I think yes.
And then you just capsulate it, and then
Yes.
it enhances
Right.
it much more.
Right.
Because it's somehow
Yeah.
oriented.
Right. Yeah, exactly. Yeah.
And then one of the second question is that when the separation between the acetylene with the acetyl,
Yeah.
the double bond, the triple bond.
Right.
So what is the basics for that? Why it's in terms of the size, I don't see that much differences.
Actually, acetylene is a linear structure, so the size is slightly smaller. It's about 3.4. But
Okay.
acetylene is a little two bench,
Yes.
so the size is a little bit larger.
Oh, that's because of the size. That
Yes,
you would do.
exactly.
It's not because of because acetylene you have a triple bond that
And
you may have
mainly,
much more paper.
mainly, yeah. But depend on different case. That's more for 74 case is triple bond, double bond also play a role because
Okay.
triple bond bind with open middle size.
Yes.
So, but in our examples, mainly is the sieving effect.
Okay.
Yes.
Thank you.
Any more question? So, please.
You were talking about the stability of the material
Mhm.
throughout your presentation. How stable it is now for any of the applications have used it, or is it usable now to be commercialized or whatever?
That's always a kind of a challenging question. It depends on some material, not strictly not stable, particularly in moisture, but it can be protected to a certain extent. And also now there are some very stable material, particularly Omar Faha. They are working on the zirconium or titanium one. They are very, very stable, actually, even stable in acidic or basic conditions. So,
And that does not affect the application that you intended to use it for?
of course, yeah, some are very stable, yeah.
If there is any question from the gallery section? No. Okay, thank you. So, any further question, please? So I would like to thank you again for your impressive lecture,
Yeah, thank you.
and I invite you to, I would like to invite the second speaker, because we have a problem here, and a technical problem, until this should be served. The second speaker is, her name is Shema Muhammad Ibrahim, assistant professor from Saudi Arabia. She's working, the title of her talk is The Influence of Lanthanum Oxide Doping on the Structure, Surface, and Kinetic Properties of Nanosized Cobalt Manganese Mixed Oxides. Please, you can start from your side.
هو لازم يركب الكابل، لا ركب الكابل، خليه راكب. ولا ايه؟ تقريبا. طيب. أنا مش عارف مالها.
told the organizers of the conference to be among you and allowed to participate in the first international conference in applied chemistry. And I hope all of us spend a good time and increase and exchange our knowledge through different scientific schools. Our article titled with the inflow of lanthanum oxide doping on structural surface and catalytic properties of nanosized cobalt manganese mixed oxides. It is known to all of us that mixed oxides containing transition metal oxides are used to design the catalytic materials to replace noble metal catalysts, and the mixed oxide materials are active for oxidation reduction reactions and combustion processes. So the present work aimed at studying the effect of lanthanum oxide doping of cobalt and manganese mixed oxide system prepared by co-precipitation method on its structural surface and catalytic properties. The techniques employed were XRD, EDX, nitrogen adsorption, desorption, and surface carried out at -100 and 96 degrees. The catalytic decomposition of hydrogen peroxide in aqueous solution at 30 to 50 degrees. The experimental part to prepare our solid catalyst through 3 steps. The first one, by co-precipitation method, we can prepare the cobalt manganese mixed oxides by precursor solution of metal nitrates by using sodium hydroxide as a precipitating agent at pH equals 8 and temperature at 70 degrees. After completely precipitated sample, drying process will be occurred at 110 degrees. The second step to prepare the doped solids with 3% of lanthanum oxide doped, 0.75, 1.5, and 3 more percent by impregnation method. The last step was the calcination for all pure and doped solids at 3 temperature, 300, 400, and 500 degrees. The results and discussion in the X-ray investigation. This figure represents the X-ray diffractograms of pure and variously doped solids calcined at 300 degrees. From the results of this curve, we can conclude that the line which appeared refer to the compound manganese CO2O4 with the unreactive cobalt 3O4 as in this figure. These mixed solids, manganese and cobalt oxide formed through the chemical reaction between cobalt 3O4 and MnO3 at temperatures range between 300 and 500 to obtain cobalt 2 MnO4. Increasing the calcination temperature to 500 for the all solids led to increasing the peak area of the main peaks, cobalt 2 MnO4 and cobalt 3O4 as in this figure. Also, the presence of lanthanum oxide don't get any peaks in these curves. This refers to the lanthanum in this case or in these solids act as a dopant, and there is no reflection lines referred to it. Also, it is clear from these figures that increasing the dopant concentration from 0.75 to 3 mole percent of lanthanum oxide led to decreasing the big area of the mean surface, cobalt 3 MnO4 and CO3O4. This result may be due to the retardation effect of lanthanum oxide, which might be attributed to the dissolution of some of lanthanum oxide cation in the loss of CO3O4. Assuming that cobalt 3O4 consists of cobalt cation exists as equivalent or tetravalent states, the dissolution could be simplified according to these equations, which refer to the divalent cations converted into trivalent ion. This means that the concentration of divalent and tetravalent cobalt cations converting into cobalt 3 ions, these trivalent didn't participate as a whole directly in the formation of CO2 MnO4, which involved divalent cobalt and trivalent manganese cations. Also, the crystallized size for different solids was calculated by using Schiller equation. And the crystallized size of the main phase cobalt 2MnO4, adding this table, refer to the doping process on silicon oxide in the range between 0.75 to 3 mole percent, lead to decreasing the crystal size as a whole. In studying the surface characteristics of the prepared solids, nitrogen adsorption desorption, as you said, measured over pure and variously low solids calcined at 500 degrees, or isotherm refer to that the adsorption process as Brunauer classification was type 2 with small hysteresis slope, and the pore volume distribution curve for pure and variously low solids calcined at 500 refer to that all the peaks, all the solids, pure and low, exhibit bi-model pore volume distribution, except the heavy load was tri-model distribution. In the surface characteristics for different solids, the surface area and total pore volume were calculated, and these tables refer to the results for pure solids and load one. Increasing the calcination temperature led to increasing the surface area and total pore volume. But doping process with 0.751% of lanthanum oxide led to the opposite effect, led to decreasing the surface area and the total pore volume. But when main pore radius were calculated for all pure and low solids, refer to that all the solids prepared was mesopore structure. In studying the energy dispersive X-ray analysis of our prepared solids, the bulk and surface contents of different ions exist in these pure and doped solids were listed in this table, and we can conclude from this result that, number one, for all samples, by increasing the concentration temperature, there is increase in the concentration of manganese species for all solids. Number two, for all solids, the percentage of cobalt cation present on the surface was much lower than that in the bulk. This may be due to the precipitating of cobalt hydroxide in the co-precipitation step in the experimental was more earlier than manganese hydroxide. Number three, doping process with 0.75 more percent for the lanthanum oxide led to increasing the percentage and the concentration of manganese species on the surface, but further increase in the doping process to 1.4% or 3 more percent led to decrease in the concentration of manganese species present on the surface, which increased progressively and the dopant content was increased or was active. Also, it is clear from this result that lanthanum percentage on the surface.
2 minutes.
What is happening? Okay. I will finish. In studying the catalytic activity of pure and variously doped solids, the first order plot of catalytic decomposition of our pure and variously doped for solids calcined at 300 and 500, we can conclude from this figure that the sample of doped solids 0.75 more percent lanthanum oxide was the most catalytically active, which may be due to increasing the concentration of manganese species on surface and decreasing the crystal size. But further increase in the dopant percentage led to decrease the catalytic activity, which may be due to decreasing the percentage of manganese species on the surface. Increasing the calcination temperature to 500, as this figure B, led to increasing the catalytic reaction activity, which may be increasing the surface area as it was obtained in the surface characteristic. In studying the activation energy for the catalytic reaction carried out at different temperature, delta E values for the calculated samples show that all the pure and variously doped solids, delta E values decreased by doping process. This trend was run parallel to the observed increase in the catalytic activity. On the other hand, increasing the doping concentration above 0.75% increased delta E value, which remained almost smaller than delta E values measured for pure catalyst samples. The conclusion for the article, the role of lanthanum oxide doping on structural surface properties and the catalytic activity was investigated. Cobalt 2 MnO4 at the measure phase was formed. 0.75% lanthanum oxide doping on manganese and cobalt oxide calcined at 500 degrees were the most active catalyst toward the hydrogen peroxide decomposition. Increasing calcination temperature and doping process led to increasing the concentration of surface manganese as active species and change in surface area or decreasing the crystal size of the main phase. Thank you.
Okay, thank you for your lecture. And now open the gate for the questions. Do you have any question in your section? Gary section, do you have a question? So, questions?
I have one question.
Okay, please.
Regarding the active sites, you are working on manganese and cobalt mixed oxides. So, what's the real active site? Is it cobalt 2, cobalt 3, or is it manganese 2 or manganese 4, or is it cobalt 4 or manganese 2, cobalt 3? Do you have any idea about this? Or
Yes, all of them are active site, but the most active site for this catalytic reaction is manganese. So the presence or the absence of manganese species has much effect on the catalytic activity.
The question was, how did you know the oxidation state of the active species? Is it separate manganese with different oxidation state, or cobalt, or spiral structure if you have?
or different,
That's from X-ray diffraction. As in this figure in the X-ray diffractogram, the peaks or the diffraction lines refer to the oxide, which is the oxidation state.
No, I mean, you have an idea which is the more preferred sites. I mean, the start of, if I have, for example, only cobalt oxide, CO3 or 4, so the active sites will be a redox cycle, including reduction or redox cycle from cobalt 2 to cobalt 3, and then reduction of cobalt 3 to cobalt 2. So, what's the rule of manganese, or adding manganese? I mean, do you have, I mean, you can think in another way. I mean, you can prepare another series of catalysts by varying the cobalt and the manganese ratios, and by for the most active catalyst, which contains the 0.75 mole lanthanum oxide. So by this way, you may be able to identify which is more active. Is it cobalt or manganese? Thank you.
Okay, thank you for the comment and the question as well. Any further question? So I'd like to thank again our presenter, Dr. Shamat. Thank you very much.
Thank you.
So our next speaker again, we return back to Professor Baha Abu Zaid, the colleague at the Chemistry Department, King Abdulaziz University, to present us for the talk and investigation of alkali cations doped nickel oxide catalyst for nitrous oxide direct decomposition.
Okay, thank you. Thank you, everyone. Assalamu alaikum and good afternoon or good evening. Thank you for your or for the King Abdulaziz University for giving us this opportunity to present our work in this first international conference. My talk will be an investigation of alkali cations doped nickel oxide catalyst for into direct decomposition. The The presentation consists of introduction, experimental. Yeah. It's not
Okay.
appearing,
Okay, so
so we have to ask some assistant. One more time. One more time.
could you change it to computer one, please? They have the remote upstairs. Just instead of screen 2, screen 1.
Screen 2 to screen 1. Now, is it working? Working? Not yet. Okay. اوكي، اتصل بيهم بتاع القاعة، يتصل بشطر الطالبات فوق او الفنية اللي فوق. ممكن ما هو دي مشكلة تغيير الداتا شو من مكان لمكان او من بس كويس كده المحاضرتين يبقوا ورا بعض يعني. معنا وقت اصل مفيش حد ورانا. خلاص ما احنا المحاضرة دي واللي وراها وخلاص. ترنج الجرس بقى.
Please let us know when you are ready. Yeah.
Here is working. It's working upstairs. Yeah, I mean. Now it's ready? Okay.
Now it's ready. Okay.
So the content of my presentation consists of introduction, experimental results, summary, and conclusions. I'll start with the introduction. When we speak about nitrous oxide is emitted from different man-made sources as well as the natural sources. But when we are speaking about the man-made sources, it's mainly nitric acid production, adipic acid production, biomass combustion, land cultivation and fertilizers, fossil fuels, and the non-selective catalytic reduction of NOx. Regarding the concentration or annual concentration of N2O now, it's the concentration is around 0.32 ppm, but it's expected that this concentration will increase approximately linearly within the next few years or next decades. So this gas has several harmful effects, including that it's considered as one of the greenhouse gases. Also, it contributes to the ozone depletion according to this equation. N2O causes also the formation of acid rains, and finally the oxides of nitrogen are combined with the hydrocarbons and sunlight. They produce the so-called photochemical smoke. Regarding the greenhouse gases and the location of nitrous oxide is considered as the third greenhouse gases. The first one is for sure the carbon dioxide, the second one methane, and the third one is the nitrous oxide. However, the concentration of nitrous oxide is very low comparing to the CO2, but its global warming potential, I mean the global potential of warming as a greenhouse gases is around 300 times compared to the CO2. So the effect of N2O, I mean 1 ton of N2O has the effect of around 300 ton of CO2. That's why there are many delegations in the United Nations conferences about the climate change and climate control. The most famous one may be the Kyoto Protocol. In that protocol, most of the countries all over the world are asked to minimize their N2O emissions by the value between 5 and 8%. And our developed countries are asked to make a reduction of this gas with about 5%. If we look to this map, one can see here clearly that most of the world countries signed the Kyoto Protocol. Kyoto Protocol asks these countries to reach the targets of 5 or 8% by the year 2012, and we already passed that time. That's why after that protocol there are many conferences of the United Nations regarding the climate change, and there are many delegations, and for example the European Union were trying to increase these values to around 25%, but till now there is no final agreement that can replace Kyoto Protocol. Since we are in Saudi Arabia, we had to know the situation of Saudi Arabia in this protocol. Saudi Arabia has signed the ratification of acceptance of Kyoto Protocol in 2005, and this for sure ask us to start our research regarding the minimization or reduction or abatement of N2O emission. I mean to take part in that type of research that is carrying abroad. Regarding the possibility of or the ways of reduction of nitrous oxide, there are two main categories. The first one is the thermal destruction. The other one is the catalytic decomposition. And the thermal destruction requires high energy, high temperature, means high energy, around maybe 700 or more degrees. So it's costly. The other alternative is the catalytic decomposition, and in that category it's classified into, it has three subcategories. The first one is the direct decomposition, I mean to decompose N2O into its elements, nitrogen and oxygen. The second one is the selective catalytic reduction, I mean to use some reduction medium like CO, like hydrocarbons, as a reduction medium to decompose the N2O. The third one, or last one in this series, is the oxidation reaction. In such type of reactions, we can use N2O in other reactions like oxidation reactions, like conversion or converting benzene, for example, to phenol, or converting methane to methanol, and so on. Our work is focused on the direct catalytic decomposition. There are many catalysts tested for this reaction which showed really good activity. Some of them metals, supported metals, oxides, mixed oxides, supported oxides, and zeolites. Up to date, the applied catalysts in this type of reactions are the zeolites, especially the iron ZSM5 type, and also the mixed oxides like spinels, cobalt oxide, based oxide catalysts. Going to the second part, which is the experimental. Regarding the catalyst preparation, nickel oxide, neat nickel oxide or bar nickel oxide was prepared by the direct calcination of nickel acetate at 500 degrees Celsius, and the alkali promoted nickel oxide catalysts, sorry for the, here they are missing, they were prepared by the impregnation method, in which the required amounts of lithium, sodium, potassium, and cesium were mixed with the required amount of nickel oxide and calcined further to or at 500 degrees. Going to the experimental setup, it consists of simple setup that contains two sources here, or two gases. The first one, nitrogen as a balanced gas, and the other one is the N2O diluted in nitrogen. These gases are mixed by using, or the required amount of nitrous oxide can be fed by using two mass flow controllers that can goes to the reactor, then to the analysis part. We used in most of our experiments catalyst weight of 0.5 gram and flow rate of 200 milliliter per minute, and finally the N2O concentration was 500 ppm. Going to the results, I'll start with the N2O decomposition of over alkali promoted nickel oxide. Here, this figure represents the XRD patterns of nickel oxide, bar nickel oxide, which is in the black curve, and its alkali promoted catalyst using metal to nickel value or ratio of 0.1. Maybe in the small peak here, on magnification or magnifying this peak, we can observe small reflection due to nickel metal. The whole spectra obtained represents or reveals the presence of nickel oxide as the major phase. Traces amounts can be observed or can be detected as very, very little amount of nickel metal. Also, for the doped catalysts, on magnification, we can observe also the presence of reflections due to their carbonates. So this indicates that there is no interaction or there is no decomposition of the alkali used carbonates. Going to the activity data, nitrous oxide itself, nitrous oxide decomposition of nickel oxide or bar nickel oxide is really, it's a poor catalyst. It's showing conversion less than 5% at 500 degrees. Adding lithium to this catalyst or doping this catalyst with lithium for sure increasing the activity slightly. Going to sodium, activity increases markedly, and potassium and cesium show with the most active catalysts. So we have now to look or to try to understand what's the reason for this higher activity of cesium and potassium. Also, this table represents the T10, 25, 50, and 90 percentage, which refer to the conversion percentage. One can observe here that this is T10 decreases markedly upon adding the lithium, followed by sodium, potassium, and cesium. Comparing our results with some other results reported in the literature, using the same, I am trying to use the cursor because to let this section show the results. The last 4 or 5 rows in that table shows the activity data carried out on some other catalysts using the same conditions. So we can see that T50 values of our new catalyst is really within the range, same range, or maybe sometimes better. Going to or trying to understand the activity data variation or activity variation, we went to measure the samples by using XPS. In this figure, one can show the XPS data of bar nickel oxide in the first region, which shows the nickel 2p nickel 3x2 peaks. The main peak, which is appear in orange color, can be deconvoluted into 3 smaller peaks or sub-peaks. Also, the same figure can be, or the same patterns can be obtained for the samples containing lithium and potassium as dopants. On analyzing these data, we can see that the 3 sub-peaks can be attributed to the formation or presence of nickel 0, nickel oxide, nickel +2, and nickel hydroxide, also nickel +2. The interesting thing that, or we can see that for the nickel 0, the binding energy of nickel oxide, nickel 0 decreases clearly upon adding potassium, and slightly upon adding the lithium as dopant. On increasing the potassium ratio to 0.2, which I'm going to talk about it in a few minutes, also we can observe further a decrease in the binding energy. Also we did the XPS for the O1S spectra. We can observe the presence of 4 peaks. These 4 peaks can be attributed to the presence of unstable oxygen, lattice oxygen, adsorbed oxygen, and another adsorbed water. The most maybe interesting thing that here the lattice oxygen also decreases, the binding energy decreases upon adding the alkali dopant. In order to understand what's the idea about this, or why the reaction is promoted, let us recall the simple mechanism for N2O decomposition. The first step involves the adsorption of N2O on a catalyst surface. I mean, the catalyst surface should be able to give electron to the coming N2O, giving NO2 minus. This N2O minus in the second step decomposes, giving N2 as a gas and adsorbed oxygen. So upon decreasing the binding energy, so sorry, this should be for the if you let us recall the nickel metal here, this one, upon adding this potassium or lithium, one can observe a noticeable decrease in the binding energy. This means the nickel metal now in this state contains or has the more ability to give electrons. That's why this equation now is the first equation is facilitated in the presence of the added alkali cations. If we are using bar nickel oxide, the obtained data. Sorry, if we are using bar nickel oxide, the added or the adsorbed N2O will accumulate on the surface and stop the reaction. That's why the addition of alkali promoters enhances this reaction. And regarding the last step, from this table we can also observe that the lattice oxygen also decreases, means the ability of the catalyst to liberate oxygen also enhanced by the presence of this added alkali cations. I have 2 minutes only. 1 minute, okay. Pointer? Yeah, okay. So we went now to the study the effect of the second part of this presentation, which is the effect of changing the metal to nickel oxide for the most two active catalysts, which are the potassium and cesium. We check the effect of changing the catalyst, the dopant concentration. We can observe here that the higher activity was obtained for the catalyst that contains nickel, potassium, or cesium to ratio of 0.1. Also going to the XPS data, it's the same. This means we have the same phenomenon, we have the same active sites. Also we did some SIM analysis and EDX, which showed that we have only nickel, oxygen, cesium, or cesium here. I mean the concentration almost the same among the catalysts. I mean this activity increase or change is not attributable to the localization or increase or supersaturation of some cesium carbonate on some sites than the other. So the two catalysts that have the same, having the different, potassium to nickel ratio of 0.05 and 0.2, almost we have the homogeneous distribution, we can say. Going to the, I have one more slide. Going to the effect of time on stream for the most two active catalysts, we can observe that the activity of the potassium is slightly decreased upon the with time, then it stays constant till around 10 hours. Regarding cesium durability seems to be better than that of potassium. We did also the effect of changing the W over F. We can observe that increasing W over F shifts the reaction towards lower temperature for both higher active catalysts. Going to the conclusion part, doping nickel oxide with alkali cations significantly enhanced its catalytic activity during N2O decomposition. Typical activity order was the unpromoted, less active than lithium, sodium, cesium, and potassium catalysts. XPS investigation indicated the presence of nickel 0 and the nickel plus 2, and based on the observed shift in the binding energy values, we can say that the active centers for the absorption of N2O is nickel 0 on the catalyst surface, and finally changing the potassium and cesium to nickel ratios give us the information or produces to us that the catalyst with the ratio of 0.1 is the catalyst with the most performance or higher performance. And thank you. Thank you for question.
Thank you, Professor Ba, for your lecture. And now we're looking for the questions. Yeah, please.
Okay, so these are nice things. So you are treating nitrous oxide, as a air pollutant, something like that, and very low concentration of nitrous oxide, right?
Yeah, because
500 ppm, right?
Yeah, because it's already in the atmosphere, 0.32 ppm.
Yeah, I know.
So,
So the thing is that you reached almost 100% above 350.
yeah.
Right. So what is the best catalyst in this field? Can you tell me what is its performance regarding the temperature?
This depends on the way of its application. If we are using SCR conditions, so the applied catalyst now is the IRZ SM5, which is the first plant was applied in Egypt in Abu Qir Fertilizers Company, and it was supplied by Group Uda from Germany, and they are producing tons from that catalyst. If you are using also direct decomposition, they are cobalt over Syria, which is used in Czech Republic by Professor Opalovo.
Okay, so another questions, I have 2-3 questions, so I just need to clarify. You are saying that you have water in the system. How come?
No. The XPS indicates the presence of adsorbed water
How come?
from the atmosphere.
Okay, so in your reaction system, you do not have any waters, right?
Yeah.
Right, so
For
you do
sure.
not have any influence of water
No.
in the reaction system, right?
No. But if we want to work on real conditions, like nitric acid production, now we have project. We are in the final steps of that project, and we were able to make setup for N2O, which give us the
So you're trying
availability,
to make
yeah,
a water resistance catalyst, or you just want to focus on reductions?
No.
Oxidation. What
Our target is to develop new catalysts, okay, that can work on real conditions like nitric acid manufacturer. So using that reaction which we have already, it's already installed, we will be able to use N2O concentrations till 3000 ppm. Also, we will be able also to introduce some NO, which is usually comes from the, which is usually comes with the emittance of during the nitric acid manufacture. Also, we will have the facility to feed some water vapor or oxygen. So we are working
Okay,
to,
so
we will
initially
work
I
at the
thought that
conditions.
you were presenting as an air pollutant removal
Yeah,
catalyst, basically.
some research groups are focused mainly on N2O as
Pollutant.
pure, as a pure or as the only reactant.
Okay. So another thing, you didn't say about anything about your particle pore size distribution or the surface area? Because you have catalytic reactions, and it's very important. And it's a bulk catalyst.
Good. Yeah,
and
yeah.
you are saying that this bulk catalyst is going
Yeah,
to be
yeah,
an
it's
industrial
good.
catalyst.
It's a good question.
It's really
We did already surface area. We did only surface area measurements. So the surface area of nickel oxide around 24 meters square per gram. It's very low. It's low. I mean, it's not like zeolites hundreds of square meter per gram. Also, the addition of alkali cations changing that ratio plus or minus 3 or 5 square meter per gram, but cesium decreases it to around 4 or 5 meters square per gram.
That's the thing, because these are big
Yeah.
molecules. So that will block the pores of.
But I mean, the texture investigation would be really interesting if you have something like zeolites and you are interested to know some information about diffusion in the pores, and so
why
will be
you are
interested
interested in bulk things, not in supported one?
we can go after that to the
So you
supported.
want
I
to
mean,
understand the
yeah. I
chemistry
mean,
on the
firstly,
bulk
we
things
are
and then
we
go
are
to the
introducing this type of catalyst. Then we can
why
go
nickel?
in another.
No, it comes. Why nickel? So it seems nobody. has worked
Good.
on nickel.
It's also another good question, because there are many work on cobalt oxide.
Right.
The first paper appeared on nickel oxide was in 2007 by Professor Sai Prasad in India, which was published in Catalysis Letters. Another paper in Catalysis, I think, Communication. And in that work, they did post-catalytic activity investigation, and they said that we were able to observe a change in the XRD patterns, which gives us the indication that nickel oxide is changed into nickel, or part of it changed into nickel metal. We did the same investigation. We couldn't observe any change in our XRD patterns after activity measurement.
Anyways, very interesting work. Very interesting.
Thank you. Thank you. Thank you.
Any further questions? Yeah, please.
Yeah, you had worked in the plug flow reactor.
Yeah.
Plug flow reactor you have used for the conversion.
Yeah.
No,
Want
you
me
have
to
not
go?
mentioned how the temperature is controlled for the reactor.
By using
as
temperature
well as-
controller, yeah.
Yeah, for plug flow.
Yeah, this one. Or this one. Sorry. Okay, now. وده اللي حصل. لا مش البوينتر. It's clear. No, Microsoft Security. بس خلاص. Okay. Pointer with you. Yeah. This is content. Yeah. This setup. Yeah. What's the question regarding
Yeah,
the how to
you are-
control the temperature
How you are controlling the temperature in the reactor? Yeah.
inside the reactor using temperature controller?
You
Yeah,
you are
thermocouple.
using-
I mean, the thermocouple is already inserted. We have two thermocouples. One that adjacent to the wall of the furnace itself, and the other one it's inside the reactor.
my point is-
adjacent to the catalyst bed.
So reaction is exothermic or endothermic? What we are doing basically?
We are using
Because
really.
you had not mentioned anything
it's
about
exothermic. Yeah, it's
about
exothermic, but we are using a very low concentration of N2O. So the temperature change will not be. That's like hydrocarbons, for example, combustion or decomposition.
Thank you for the questions. Now, thank you, Professor Ba, again.
Thank you.
We would like to thank our speaker.
Thank you.
And we're going now to the last talk in our session. It will be presented by Professor Azil Abu Bakr. He's a professor from Malaysia. And the title of his talk is The Investigation of Manganese Oxide-Based Catalysts for the Catalytic Oxidation Desulfurization on Model Diesel Fuel. So I'm looking forward to listen to your talk.
Inshallah.
Thank you.
Inshallah. Okay, Assalamualaikum warahmatullahi wabarakatuh. I'm the last speaker today, and I will go fast and stick to the time. So actually, was given a task by our government to solve the problems of diesel, because Malaysia has still what they call adopting Euro 2 diesel, whereby if one of the preconditions to achieve the what they call the developing country, we have to comply to the what they call to the United Nations protocol, whereby we have to reduce or what we call, we have a standard of air pollutions. Okay, and if we are still using the Euro 2, then meaning in the diesel contain more than 50 ppm of what they call sulfur compound. So actually, we have to what they call reduce the sulfur content, meaning that from Euro 2 we have to convert to Euro 4. Okay, by 2015 this year, but we cannot achieve it. So we have to extend for another maybe 2 or 3 years. Okay, because of what? Because of no technology. Not to say no technology, we have a technology, but the technology is very expensive. Very expensive. Meaning if you using the present technology, the price of the diesel will go up tremendously. So this is what I just want to present. It's not the best catalyst actually. Okay, we have to spare, and that's still in what they call the patent filing. Okay, so this is a moderate one, but it's enough to share with you the technology. It's an organic manganese base. Okay, catalyst used to what they call reduce what they call sulfur in diesel. What we call it catalytic oxidative desulfurizations. And today I would like to share with you what they have done. We have optimized. And in fact, we have studied the catalytic study. What happened actually? What's the role played by the catalyst in these reactions? Okay. Okay. This one is everybody knows about it. Okay. How to produce a diesel, produce a petrol, lubricant, and so on. Okay. It's common. Okay. This is what the major part of my talk is about diesel fuel. Okay. Diesel fuel. Actually, the compound in sulfur compound in diesel. What we call many types, but the main is a thiophene compound. The thiophene, the lowest thiophene, this side is not shown, but the major one is the 2,4,6 DMMBT, what we call benzothiophene. Okay, DBT is not so much, but in this study we concentrate on thiophene, which is this side, DBT, and this one. It's a major what they call sulfur compound in diesel. Okay. As we know, if in the diesel contains sulfur during the ignition, okay, during the ignition in the car, automobile, and system, they produce a sulfur dioxide, which is also the what they call giving the acid rain. Okay, which is not good. And in fact, in Malaysia, we still at this stage, okay, 202, and we have to adopt Euro 4 diesel by next year. But I don't think we can comply to this need. Okay, this is the what we call the charter given by International Fuel Oil. Let's see Malaysia, this one. Okay, okay, let's see Malaysia, and this is yours. Just imagine. Okay. We have to achieve this. Okay, we have to achieve, this Euro 4, less than 50 ppm. 50 ppm. Now we are around maximum 500 now, present. Okay, and actually we are working together with our national oil, what they call oil, petroleum, we call it Petronas. Like yours is Aramco, Habib, and so on. Okay. Okay. Present, the technology available is what they call hydro desulfurization. Shell is using this technology. Okay, Shell. Bio desulfurization possible, but it's not practical. For academic, it's okay. This one is also for academic exercise, it's okay. For the commercialization, put aside. Okay, so what we want to represent is the catalytic oxidative desulfurization. I mean using catalyst in the presence of oxidant. Okay, to remove the sulfur compound in diesel. Okay, basically this process, this catalytic oxidative process comprised of two parts. Okay, one is using the oxidant to oxidize. Okay, then we in the presence of catalyst. Okay, oxidation in the presence of catalyst, we call it catalytic oxidation. Then after that, after the sulfur been oxidized to sulfoxide or sulfone compound, we remove it from the what they call diesel or hydrocarbon using the what they call solvent extraction. Okay, there's so many reported articles about what they call solvent extraction of DMF, miso, acetonitrile, methanol, and so on. But we are using this because it's better. I give you why. Okay, and what they call the oxidant, we use what they call TBHP. Okay, TBHP, tetrabutyl hydroperoxide. Okay, this is the effect of the sulfur if we still contain in the diesel. Okay, okay, this is the literature about it. Many people have tried to use so many technology. Okay, for example, using ionic liquid is okay. It sounds okay for academic exercises. For practicality, I think it's a long way to go. Furthermore, it's very expensive. It's difficult to make. Okay, difficult to separate. Okay, but oxidative desulfurization is okay. It sounds okay because they are using just oxidant, no catalyst. Okay, it's still okay, but cannot achieve our target, Euro 4. Okay, and she should be this time. And in fact, at the end of the section, I will propose it should be the combinations of the process. Okay, let's see. Let's follow. Okay, the catalysts they have reported. Okay, and now I'm leading to the commercial types. Okay, meaning we have to catalysts have to be supported. There's no ways in the form of powder and so on. That is for academic, but for commercialization, for industrial use, should be supported. And the supported what they call supported material normally is this one because it's very cheap, very stable inerts and so on. Okay, so. My chemistry or my investigation is about this one also, manganese supported and this, and we use a dopant. Various dopant we have used it. Okay, okay. The presentation contains screening. We screen. Okay, just for using solvent extraction, compared to the using oxidant only, and final, what's happened if we combine those? I mean, we call it catalytic desulfurization. Okay, and we study mechanism and verifications of the product. Okay, and in fact, every step we try to optimize it using RSM, response surface methodology methods. Okay, using BBD design. Okay, that means to prove statistically whether our approach is correct or not. Okay, this is a lot. Okay. Okay, although the diesel methodology we have done, okay, oxidant, solvent, we have tried so many various types. Okay, and what in this presentation, okay, we try with the model this one model. We purchase thiophene, dibenzothiophene, and which is the common, okay, common and the dominant in the sulfur compound. And in fact, we use our commercial diesel, which at that time, when I purchased or bought it in the petrol station, when we detect it contain 415 ppm. At that time, it's fluctuating. Sometimes until 550, sometimes go to 4 around these figures. Okay. Okay, just have a look at these optimizations of EDS, I mean solvent extraction, only with the diesel, and ODS, oxidative desulfurization technique. Okay. Okay, this is the result. Okay, you use solvent DMF. Okay, ratio of the solvent 1:1. Okay, extraction we just shake it 30 minutes. Temperature this one. Okay, in fact we have tried 20, 40. We have tried it. Okay, and this one is the recommended. And what we found is this one. Okay, if we use a modern diesel, we can achieve 90%, more than 90%. But if this one is quite stubborn. What's happened is the aromatic, the bulky aromatic is quite difficult. What's happened now? The technology they use by Shell company, okay, they cannot delete or eliminate this. It's very stubborn. Okay, that's why we introduced the catalytic dispersion, so that we want to cater this one. Okay, let's say for this one, just add in what they call solvent extraction, shake it. We can remove most of the lower what they call sulfur compound. Okay, for the commercialization for the commercial diesel of our Malaysian diesel, okay, we just managed to get 67% only. There's around 1/4 the remaining for the first extraction. We can lower down until achieve the 0.4, but so many extraction we have to done it, and it's not cost effective. Okay. Okay. This is when you compare with the RSM, okay, optimization technique. Okay, what they propose is if we use this parameter, only set 83, but experimental prove that we get higher than that. Okay. Okay, for oxidative, okay, we use TBHP, okay, third butyl hydroperoxide with these conditions, okay, and by using this, meaning we add oxidant, reflux, or we put some heat in it, about 45, okay, for 30 minutes. You can remove this. Sorry. Okay, can remove so much. Okay. Okay. This is proposed by the by the aesthetical RSM, but we just experimental. We just managed to so small. Okay. So small. This is oxidative, using oxidant. After that, we have to use a solvent extraction also, okay, to remove the oxidized sulfur compound. Okay, so we can achieve it. Okay, so what happened? We try to use catalytic oxidative desulfurization. Okay, and here what we did, okay, we try with all sort of base compound, base metal oxide. This is metal oxide, okay? And we found that this is potential. Manganese and cerium is a potential. Okay, so from this we just stick to this one. Okay, for this presentation. Okay, we use a manganese on supported on and we use a dopant. Okay, all sort of dopant we use it. Okay, okay. This is a base manganese supported on knee, and you use dopant. We study a dopant. Where is dopant on this manganese supported alumina? Okay, we found that iron is quite potential for this one. Okay, it's quite potential. So from that we start to prepare our catalyst using the impregnation method. Okay, and we try to play around with the ratio of this iron and manganese, and we found that 10 to 90 give the promising or the potential catalyst. Okay, whereby we managed to remove more than 90%. Okay, more than 90% of the sulfur compound. Okay, we try play around with the temperature. It showed that 500 is the best. With the catalyst dosage, okay, give a 12 gram per liter, okay, per liter of the sample, okay, experiment, and can give a cycle for five cycle without any deterioration. Okay, this is using the RSM, and it showed that give a 55%, but the experimenter showed 52.7%. Still not good. Yeah? But what we prepare, this one I think no need to discuss. Okay. This is a mechanism. We study a mechanism. What happened actually? In our catalyst, ferromanganese, what happened when we add oxidant, and here is the model. This we use an octane. It's a standard. If we add into the what they call the catalyst, what happened? Only the oxidant absorbed on the surface. Okay, you see, absorbed on the surface. At the 30 minutes, okay, at the 30 minutes is very high. After that, low, decrease, meaning that this is the maximum absorption of the oxidant on the surface. Then after that, it dissociates to form the active species, and then react with the sulfur compound to form the sulfur oxide or sulfon. This is, okay, we monitor it using a GC, okay, whereby at first they form sulfur oxide plus sulfon, but later on, as the time goes increase, we can see that sulfon is the major. Okay, then we remove it using the solvent extraction using DMF. Okay, so this we propose the mechanism. By all the data we obtained, we propose the mechanism. Very simple mechanism. Okay, and what we propose is there should be, to achieve the Euro 4, okay, should be the combinations. That means first we have to do extraction. Secondly, we have to do the catalytic oxidative. Only then we can achieve this. Sulfur compound from the original 415 ppm to 51, 41.5. Okay, it's more than 90%. This is the physical features of our treated and the standard Euro 4. Is almost better, we found. Okay, I think this is a test we have done it. Okay, with respect to the CO, much better of the treated one. CO2, okay, much better with the treated one, lower. And NOx, right, or fan, okay, lower, and also SO2, lower. That's what we found. Okay, I think that's all. Okay, that's all. Okay, and this is the result. And this, by using this technique, we hope that we can easily or give a Euro 4 in a cost-effective manner. I think that's all to share with you all.
Okay, thank you for your impressive lecture. And now, open for discussion and questions. Any questions from our audience? Any question from? Yeah.
Thank you, Professor, for your presentation. In fact, can you cite the reason why the Malaysia is lacking in terms of implementation of the Euro 4 diesel so far?
We have the technology. We want, if we would adopt the Shell technology, hydrothermal.
Hydrodesulfurization, yeah.
No, we can afford. We can afford to buy diesel. Very expensive. Very expensive, brother.
And moreover, in the first step, as you had mentioned in the EDT, that you are reducing the sulfur level in the diesel by 136 or so. Whereas from the oxidative process, we have written from 90 onwards to 47, something like that.
Yeah.
What about in between 137 to 90?
137, 90?
Yeah.
I can't catch you. Oh. Can you?
Yeah, from the first EDT process, we have just mentioned.
EDS,
you are reducing the sulfur level from 437, something like that, to 136.
130,
ppm, yeah. And in the oxidative process, we had written from 90 to 47.
90, 47, no.
Yeah, from 90.
Okay, hold on.
Next.
This one,
No, next.
This one?
No, next.
No.
Where you had make the comparison of EDS as well as
Okay.
oxidative process.
Yeah. This one is a model. When it comes to the real diesel, we have so many constraints. In the real diesel, we have so many constraints. So it will affect the reaction actually. This is a model just individual.
Oh.
It's a neat process.
So you have taken only dibenzothiophene DBT.
Yeah. In octane, very simple. Yeah.
Have you tried your catalyst in using a real diesel?
Yeah. This is Malaysian diesel, commercial diesel.
Okay.
Yeah. This is a Malaysian diesel. The present Malaysian. Yeah, we use both to compare.
I have a question regarding the type of reactor that you are using. It's conventional. I mean, it's a flow rate reactor, or it's.
No. We just doing a very crude experiment. The maximum volume is 1 liter only.
Mm-hmm.
Okay. Actually, we try already design what they call the process setup.
Okay.
On the way.
On the way to set up.
A system.
So it's batch reactor.
Yeah, like something
It will
like
be
that.
batch reactor.
Yeah, batch reactor or mobile one, whereby we can bring to the site for the process.
Okay.
On the way, on the process.
Okay.
Yeah.
Any further question? A girly section. Any question from there? Okay. So I would like to thank you and thank all of you for the attendance of our session. And I would like to say we close for today. Thank you for everyone here.